All right, guys. So in this video, I'm going to be taking notes on section 9.3, which is just tests about a difference in proportions. You'll note that these notes technically also cover pages 27 and 28, but I decided to just skip ahead so that way we can save time on the video to page 29. It's basically the same thing as 27, 28. Just this example here goes over a difference in proportions, but it also includes the four-step process, which I think is the most important. So this is on page 29. Now, a difference in proportions is essentially the same exact thing as just a single proportion. It's just your formula is going to be slightly different. You're going to have to check conditions for both groups. And that's about it. There is one special thing that we're going to be talking about here in a little bit. But let's just take a look at this example here. So it says, which grade is more likely to go to prom? So we've seen this example before, but it says at many high schools, the prom is an annual dance that only juniors and seniors can attend. The student council at a large high school is wondering if juniors or seniors are more likely to attend the prom. They take a random sample of 50 juniors and find that 28 are planning to attend prom, and an independent random sample of 45 seniors reveals that 29 are planning on attending. So it says, is there convincing statistical evidence that a higher proportion of seniors are going to prom than juniors? Use a 5% significance level. So first thing I want to point out, so we know that there are 50 juniors, and out of those 50, 28 are planning to attend, 45 seniors, where 29 are planning to attend. So what I'm going to do, I'm going to say p hat 1. I'm just going to write these down right here real quick. So p hat 1 was 28 out of 50. That's the same thing as 0.56. And then p hat 2, that was 29 out of 45. It's the same thing as 0.644. Okay, so that's going to be my seniors. Now, for the choose section, okay, there's a few things that we need. We need to name our procedure. We need to show our parameter, define it. We need to state our hypotheses, significance level, which is already filled in for us, but we need that in the choose section. Calculate our statistic, and then evidence for the hypothesis, right? And I wrote these up here just because it makes it easier whenever we go through it, especially when we get to the statistics section, we already have our proportions. But we are doing a significance test for two samples, right? Got samples of juniors and a sample of seniors. So my procedure name is going to be to sample Z test for P1 minus P2. Remember, it's P1 and P2, not P hat. P hat was the sample we got, but we want to estimate this for the proportion, or for the population proportion. So it's P1 minus P2. Now we need to define that parameter. Okay, P1 minus P2, what does that represent? Well, it represents the true difference in proportions of who go to prom. And in parentheses, I'm going to put junior minus senior. Anytime you have a problem like this where you're doing a difference, you need to define your direction. So junior minus senior is what I'm doing. If you did senior minus junior, you would need to make sure you write that. And now your hypotheses. So anytime you're writing a hypothesis, typically your null hypothesis represents no difference. Okay? So if there was no difference between juniors and seniors, well, P1 minus P2 would just be equal to 0, right? And then your alternative is where you see a difference, right? So P1 minus P2 is something else. Well, based on these two proportions here, 0.56, 0.644, it looks like we have more seniors going than juniors. So if I'm doing P1 minus P2, based on our sample, it looks like it should be less than 0. Because if I subtract these, I would get a negative number, right? Another way that you might see these hypotheses written, some textbooks, some writings might have it as, instead of P1 minus P2 equals 0, they might move this P2 over, right? And it becomes P1 is equal to P2. Same with the alternative. You might see it as P1 is less than P2. All right, significance level, already at 0.05. Your statistics, so we want to calculate the actual difference we saw in real life. So P hat 1 minus P hat 2, well, that's equal to 0.56 minus 0.644. That's going to give me a difference of negative 0.084. And the evidence for it, how do I know, or how do I feel, or why do I feel that seniors are more likely to go than juniors? Well, P hat 1 minus P hat 2 was negative 0.084. Well, just negative 0.084, right? Well, that's less than 0. So that's my evidence to suggest that the alternative is the one that's actually true. But from here, we want to actually see if there's significant evidence, okay? All right, now, checking your conditions, okay? Remember, we got random, 10%, and large counts. So random, anytime we're doing this for two proportions, we got to check the conditions for both groups. So the first one was random, okay? And if we go back up to the problem itself, it says they take a random sample of juniors and an independent random sample of seniors. So I've got independent random samples. Okay, so that one's good. For the 10% rule, remember I got to do this for both. Well, we had 50 juniors. It's safe to assume, if this is a large high school, that's less than or equal to 10% of all juniors, right? And then we had 45 seniors. Again, safe to assume that's less than or equal to 10% of all seniors. And then the last thing is large counts. Now, this is where it gets a little bit different for a difference in proportions. So normally, we would just have n times p, n times 1 minus p, and we would do that for both groups, right? P1, and then we do it for P2. Well, if we're assuming, remember, going all the way back to our null hypothesis, if we're assuming that there is no difference between juniors and seniors, then it really theoretically doesn't matter if we pulled 50 juniors and 45 seniors, or if we pulled 45 juniors, 50 seniors. Theoretically, these two groups are the same. So instead of having two different proportions, what we're actually going to do is we're going to combine these proportions. We're going to create what's called P hat C. And this is just your first fraction plus your second fraction. So I got the numerators added together on top, my denominators added on bottom. So juniors were 28 out of 50, seniors were 29 out of 45. So I'm going to have 28 plus 29 over 50 plus 45. And so when I add those together and divide it out, I'm going to get a P hat C of 0.6. So when I calculate my large counts, this is the proportion that I'm using. Okay? So I'm going to come back down to my large counts. So I have to show that N1 times P hat C is greater than or equal to 10. I have to show N1 times 1 minus P hat C is greater than or equal to 10. And then I have to do it again with N2. So N2 times P hat C is greater than or equal to 10. N2 times 1 minus P hat C is greater than or equal to 10. And remember, we're doing this really because we're assuming that both proportions are of the same probability of likely or not likely going. And so when we do that, we have to assume essentially we're pooling these groups together and we're saying, okay, 45 over here, 50 over there. What are the odds that, or what proportion of this group goes, what proportion of this group goes? And so that's why we kind of have to, we're doing that all the way through because we have to assume that they're part of the same group. And so N1 is 50 times 0.6. That gives me, what is that, 30? That's greater than or equal to 10. And then I'm going to have 50 times 0.4. That's equal to 20, which is greater than or equal to 10. And then I'm going to come over here. I had 45 times 0.6. That's going to give me 27, which is greater than or equal to 10. And then 45 times 0.4. That equals 18, which is also greater than or equal to 10. And so I passed random, I passed the 10%, and I passed the large counts. So just remember, when you're doing a difference in proportions, a significance test for a difference in proportions, you have to use p hat c. If you do p1 and p2 or p hat 1, p hat 2, it's going to be incorrect. You're going to get different numbers, okay? All right. So next part is calculate. So again, general formula is the same thing as one proportion, okay? It's just the z-score formula, right? So test statistic is equal to your statistic minus your parameter divided by your standard deviation. And if I plug everything in, well, our statistic is p hat 1 minus p hat 2. That's what we calculated earlier. Okay. Minus p1 minus p2, which in this case we assume was 0, right? All right. And then divided by the standard deviation. So if I'm doing a standard deviation for a difference in proportions, normally we would have, you know, in the past we've had p hat 1, p hat 2, or p1 p2. Again, we're using that combined value, p hat c times 1 minus p hat c divided by n1 plus p hat c times 1 minus p hat c divided by n2. Remember, we're just assuming that these groups are equally likely to go, so we've basically combined their probabilities or their proportions. And then from here, I'm just plugging in, right? So statistic was negative 0.084. Our assumed difference was 0 divided by the square root of 0.6 times 0.4 divided by 50 plus 0.6 times 0.4 divided by 45. And if I calculate all that, I'm going to get negative 0.84. Kind of a coincidence that it's only one decimal off of this, but negative 0.84. Now, if I draw a picture, different ways you can draw it. It's still going to be a normal curve, right? If you want to, you can do yours with real numbers, or you can do the standardized graph. I like doing the standardized graph. Again, you can do whatever you like, but I have negative 0.84, and I'm shading in all of this stuff. And then remember, we got to give it a name. It's a normal curve, which in my case, since it's a standardized graph, my mean is 0, standard deviation is 1. Test statistic, z is equal to negative 0.84. And so if I calculate my p-value, do a normal CDF, my lower bound is negative 9999, upper bound is negative 0.84, mean of 0, standard deviation of 1. Again, if you did normal values like real life values, your mean here would be 0, and then your standard deviation would be something different. In this case, it would actually be 0.10 instead of 1. But if I calculate all this, I'm going to get a z-score of, a p-value of 0.20, so about 20% chance. So, in my conclusion, remember I need to interpret my p-value and then make a decision and conclusion. Remember, we always assume the null is true until proven otherwise. So assuming the null is true, in other words, p1 minus p2 is equal to 0. There is a 0.20 probability of getting a p1 minus p2 of negative 0.084 or less purely by chance. And since we're doing a significance level of 0.05, okay, significance level of 0.05, 0.2 is bigger than 0.05, so that means that it's likely to happen just by random chance, right? 20% is a pretty common occurrence. So I would say since 0.2 is greater than 0.05, we fail to reject the null. And do not have convincing evidence that a higher proportion of seniors go to prom. And just remember, whenever we're writing our conclusion, you never say, we say fail to reject. You never say accept. Remember, we assume that the null is true until we have enough evidence to prove otherwise. So you can't say accept the null if it's already your basis. It's already accepted before you even do anything. So we say we fail to reject. We cannot prove, or let's say we cannot disprove the null hypothesis. Okay, so we interpret our p-value and then we make a decision and conclusion. The biggest takeaway here, obviously, do your conditions for both groups, okay? And then also make sure if you're doing a significance test for a difference in proportions, you have to do p hat c, okay? P hat c is the big thing, all right? So, a couple of quick notes. So for the 4C method, the biggest differences, so in the choose section, it's all the same requirements. The big thing is just the name. So since you're doing 2 samples, it would be a 2-sample z-test for p1 minus p2. In the check section, you have to do conditions for both groups. in the calculate section. The formula is slightly different. It's still the same exact formula. It's just you plug in different values. So p hat 1 minus p hat 2 minus p1 minus p2. And then on the bottom, that's where you see that combined proportion. So it's the square root of p hat c times 1 minus p hat c over n1 plus p hat c times 1 minus p hat c over n2. And then the conclusion is pretty much the same thing. Once you have your p-value, it's basically the same thing. So you just interpret p-value. And you make a decision. If I can spell correctly. Decision and conclusion. All right, so your main goal, I would definitely do the check your understanding. It's another one of those free response type questions that kind of goes over the same exact stuff that we just did. It's going to be a difference in proportions. So that way you can test yourself on this stuff. And then I would try and do it as much as you can without checking the key. Once you're done with it, you can scan that QR code in your notes. You can check the key, see how close you got to it. Remember, whenever you're doing these, write out the word choose and box it off, and then put all your stuff, and then check, box it off, do all your stuff, and then so on and so forth for all 4 sections. It helps organize it. It helps not only you figure out what you have left to complete, it also, like for example, on the AP exam, whenever they go and check it, like grade it, they're going to look for all of those things. Organization makes it so much easier for you to get the points that you deserve whenever you go and turn your stuff in. All right. So try and do this stuff as much as you can without your notes, without any help. Then check your key, see how it is. If you have any questions, feel free to let me know and I'll be able to help.